Hello and welcome to episode 9 of the Note Card Review. Today's topic is bonds. Atomic bonds, molecular bonds, take your pick. So, the one core goal of creating a bond between different atoms to create a molecule or to do anything related is to balance the valence electrons in the atom. So for some elements, this will be preferentially losing electrons or largely sharing them with someone else and kind of giving them away. And for other elements, this will involve pulling electrons towards oneself and keeping them on your atomic structure most of the time. There are really three different big pathways to accomplish this mission. One, ionic. Okay, so ionic is getting the Thieves Guild to help out. It's going to create ions, not actually molecules, because those electrons are actually moving to the other atom, not being shared between the two. In order for this to happen, you're going to need a big electronegativity difference between the two different elements. Okay, so for example, sodium and chloride. Okay, those sodium and chlorine, those two elements have a large electronegativity difference, so the chlorine is going to pull the electrons completely to itself. There are two different types of covalent bonds that offer pathways to accomplish this mission. Nonpolar covalent is kind of like your wife being a spy too. So it's equal sharing of the electrons, and it requires a small or zero electronegativity difference, the electrons being shared back and forth constantly and equally between the atoms. You can also form polar covalent bonds. This is like having a getaway driver. Okay, it's unequal sharing. One person's getting a lot of the credit and doing a lot more work, and in this case, pulling the electron towards itself. It requires a fairly large electronegativity difference. This is kind of the middle option between nonpolar covalent equal sharing and complete lack of sharing with the ionic theft. Okay, so we see this with elements that have between a 0.5-ish and 1.4-ish level of electronegativity difference. The reason there is some leeway or flexibility or uncertainty on these values is simply because of the variability of the elements and kind of the strictures, the requirements on what we say is ionic versus polar covalent. But these are good numbers for y'all to work from. You've also got the side quest, okay? You can get distracted with hydrogen bonds. Okay? Hydrogen bonds are forming in between molecules or within molecules. They can do both. Okay. And it really is just a side effect of partial charges on polar molecules that have hydrogen, because hydrogen is not very strong at all when it comes to electronegativity. So it is not almost always, but it is very often going to end up in polar covalent bonds where it has a partial positive charge. We see this in organic chemistry with basically everything except hydrogen-hydrogen and hydrogen-carbon bonds, because they are close enough together that it forms a polar bond. But everything else, you're going to have hydrogen having that partial charge. Okay, if we take a look at a few quick targets on how this actually works, okay, I'm going to show you how these different molecules connect very briefly, and you can dive into the details on your own. So, simplest first, we have H2O. Okay, so we've got our oxygen here, and we know from prior discussions that it can form two bonds. Hydrogen, here in white, can only form one bond, so we have a very simple connection and only one real possibility between these three atoms. Because hydrogen is much weaker in electronegativity than oxygen, you're going to end up with a partial negative charge over here on the oxygen and partial positive charges on each of the hydrogen atoms. Okay, KCl. Okay, this is potassium chloride. Okay? This is a great example of where we see ionic bonds. Okay, and if you see something like this where you have metals on opposite sides of the periodic table, this is what you're going to get. Okay, and the reason for that is generally because their electronegativity difference is going to be very high. Okay, and here we have potassium and chlorine. Okay, there's a huge electronegativity difference here, and we know from looking at where they are on the periodic table or drawing their Lewis dot diagram that chlorine has 7 out of 8 electrons in its valence shell. Potassium only has 1. So there's only one potential electron to be lost or gained or bond formed for any of these. Okay. In this case, since chlorine has the much stronger electronegativity, it is going to take the electron from the potassium and end up with a full -1 charge because it took an entire electron, and you end up with the potassium ending up with a full +1 charge. Remember, the reason why this charge is negative here is because the electron itself is negatively charged. Okay. Here with N2, this is a nice easy example because you have perfectly balanced atoms that you're working with. So in this case, we have 2 nitrogen atoms, and we know that since that means their electronegativity is precisely matched, so this will be a nonpolar covalent bond. Okay. Here with nitrogen, we can know from looking at the periodic table, they can form up to 3 bonds. So we're just going to go all ham on this and say that they are forming 3 bonds with each other. So this would be a very strong triple bond. Rare, but not necessarily so for things like N2. And we end up with absolutely no charge, either partial or whole. Okay. Here at the bottom, we have a more complex molecule, CO2H4. Okay, and I've just drawn them in, one sensible arrangement. And this is obviously 2D, not 3D. But if we start looking at what type of bonds can potentially form between the various oxygen, hydrogen, and carbon atoms in this molecule, we know hydrogen can only form 1 bond, okay, here. And we know oxygen can form 2, so it needs to connect to something else. We connect to carbon via single bonds, because we also have 2 more hydrogen bond molecules that we need to deal with, which are connected to the carbon. Okay. If we look for charges, we know that hydrogen tends to end up with a partial positive charge, and especially if it's partnered up with oxygen, which is what we see here. And then over here on this side, we have carbon and hydrogen. Remember, this was a rare case where we have 2 elements that seem very different when we look at their electronegativities, but in this case, there's no partial charge going to form on the hydrogen because it is balanced enough with carbon that it ends up forming nonpolar bonds with carbon rather than polar bonds with carbon. The oxygen, however, responds as we would probably expect it to. It forms polar bonds both with the hydrogen and with the carbon, so we end up with partial negative charges on both of our oxygen molecules. Okay. Carbon is forming nonpolar bonds with the hydrogens here, but the bonds with the oxygen are polar, so it's going to end up with at least a partial positive charge, but it's not going to be as strong of a positive charge as if it were also forming polar bonds with the hydrogen atoms. Hopefully that helps. It's a little bit longer video than I typically do for these, but we covered a lot of topics, so hopefully this was helpful.